From the palm of your hand to the frontiers of defense, microelectronics power our world. But the industry is at a critical inflection point. For decades, innovation has focused on squeezing more transistors onto silicon chips, but the demands of emerging technologies are pushing this approach to its breaking point. Fabrication costs are skyrocketing, and we're hitting the physical limits of miniaturization. The future lies in a new dimension: 3D heterogeneous integration, or 3D-HI. 3D-HI will revolutionize microelectronics by vertically stacking and interconnecting diverse components and materials, creating high-performance systems that surpass traditional 2D technology. This innovation allows us to move beyond the limitations of silicon, integrating new materials to achieve capabilities essential for both Department of Defense and commercial applications. To spearhead this revolution, DARPA created the Next Generation Microelectronics Manufacturing Program, NGMM. DARPA is partnering with the University of Texas at Austin and its Texas Institute for Electronics Research Center to establish the TIE NGMM Center in Austin, Texas. This open-access 3D-HI manufacturing center will foster a vibrant ecosystem of innovators, from industry giants to agile startups, all working together to push the boundaries of microelectronics manufacturing. This ecosystem will drive disruptive innovation and ensure access to cutting-edge technology for national security and economic competitiveness. 3D-HI will be the engine of tomorrow's breakthroughs, driving innovation across industries and ensuring U.S. leadership on the global technology stage. Join us in building the future with NGMM.
Good morning. I am excited to have a little bit of time to talk with you this morning about how DARPA is enabling the next generation of microelectronics through 3D heterogeneous integration. But more importantly, as Whitney said this morning, I'm quite excited to hear from you about the ideas that you have, innovative ideas, creative ideas, to leverage this capability to implement new systems, new architectures, both for commercial and defense applications. So yesterday, we heard in a couple different talks the challenges around Moore's Law that we're facing, both economic as well as technical challenges. DARPA, of course, has been involved for over 50 years in driving innovation and supporting this space. And we recognize several really key waves of innovation that has driven the development of continued capability with implementing monolithic integrated circuits and really driving silicon to its limits. We believe, however, that the next wave of innovation is really going to be driven by 3D heterogeneous integration. And as Whitney said this morning to us, that really means integration of mixed materials and compound semiconductors with silicon and the tremendous benefits that you can see in doing so. So it's worth pausing for a minute as Whitney chatted a little bit this morning about, I would assert that heterogeneous integration at this point means about everything to everybody. I hear it in lots of different conversations applied to many, many different applications. So I'd like to start with this and say that we certainly recognize tremendous innovation that continues in monolithic space, again, aligned with Moore's Law, and tremendous opportunities to continue to integrate more and more transistors in monolithic solutions. But we also recognize, as I said, the challenges associated with that. So many are focused on 2.5D and the chiplet ecosystem and opportunities to integrate more and more individual chips, silicon chips, on a substrate material with the intent to continue to push that to the point that it operates closer and closer in terms of performance to a monolithic solution, but with the capability to put more and more compute power on a single platform. Still others are focused in 3D stacking of silicon and the benefits that can come from that, and in particular, tailoring and tuning each layer in a silicon stack for a specific application and really optimizing that stack and the performance that you can get there. We, with NGMM, are very, very focused on the right-hand side of this chart in enabling true 3D heterogeneous integration of mixed materials and complementing the significant capabilities of silicon with compound semiconductors, which allow us to develop devices that have 100x types of improvements in performance and size, weight, and power, and really allow us to operate in domains beyond the reach of silicon's capabilities. DARPA has been investing for well over 25 years in the area of heterogeneous integration. I think there are a couple of folks that are sitting in the audience today who were directly involved in this, were some of the initial leadership in driving these programs. Really, NGMM is the capstone of all of this development, all of this investment in 3D-HI technologies. DARPA has invested in process developments, including new materials that can be integrated into these kinds of systems, providing a different different approaches and different applications, as well as the integration technologies themselves, the way that we bond and connect these devices together, continuing to push the boundaries in performance for those architectures and for those integration approaches. One of the key challenges in doing this 3D stacking, I'll talk more about here, is really thermal. When we stack these things up and they get hot, that's an extremely difficult problem to solve. DARPA has ongoing programs now and has invested in the past in those thermal areas. And then really pushing for high performance, high speed interconnects. Also, there has been some focus on product development as well, with developmental work in the area of arrays and sensors, optical devices, ultra-wide bandgap devices, as well as some focus on helping to derive and define standards to support the integration of these systems. So if I try to break down in a nutshell what I think are some of the most significant challenges and really the innovation that's required for NGMM, I look at the tremendous creativity of many folks that are sitting in this room when it comes to new materials to help us solve challenging problems that the defense is interested in, but also have significant commercial applications as well. And when I look at that and I think about the diversity and the creativity that folks can generate with the periodic table, then coupled with a diverse supply chain where we've got materials coming from all different locations, then basically feeding into a very, very diverse set of subcomponents that would feed into this advanced integration capability that we're standing up with NGMM. So you can think of wafer sizes from 75 millimeters to 300 millimeters. We've got different thicknesses of those wafers. We've got significantly different thermal mechanical properties for each of those wafers. So we have this very, very diverse set of subcomponents coming into the front end of this integration facility. And our goal is to come up with really a small set of process modules that allows us to intimately integrate those components into these advanced 3D stacks. But coupled with that is really the fact that, in the good old days, my background is analog IC design. And in the good old days, I used to just make certain that what I was designing would meet the electrical performance parameters and toss it over the fence and hope for the best for the fab side and for the packaging side and ultimately implementation. But for these 3D stacks, really the intersect of this Venn diagram that I have here, where developing a reliable microsystem doesn't just mean that you can meet the electrical performance parameters that are there, but we really now have the need to do true co-design, where we're looking at making sure we have mechanical integrity and that we have thermal stability long-term. And really the only way that we can deliver a reliable microsystem in this space is to ensure that it meets all of three of those simultaneously. So we're pushing the boundaries a bit relative to the development of assembly design kits and even the EDA tool flows to support these kinds of integrated systems and make certain that we can build and field reliable systems. And I'll talk a little bit more about what that means for us and what it means to deliver a reliable system and why that matters in the context of NGMM. So now in a nutshell, what is this going to look like? What's the vision? How are we going to stand up this capability and what's the plan? I'm going to start to dig now into some of the details of how we're going to implement this vision, where we are today and kind of where we're headed, and then ask for your future involvement moving forward. This is on a single chart, really a summary of where we're headed, the capability that we're standing up. We have selected the Texas Institute for Electronics. You got to see some nice video footage of that in the video this morning as the performer to implement NGMM on behalf of DARPA. They're standing up this advanced integration capability that's meant to be a foundry service. So it's going to be broadly available, not just for defense applications, but really intended to allow innovation in the commercial sector and also for dual use applications. So really the front end of this in terms of the partners and the customers that'll be working with us really span industry through academia as well as government. And then the range of TRLs, or kind of the range or the span of the scope of work that we intend to pursue, is really all the way from fundamental research in new processes and techniques to integrate and bond these devices together, as well as new equipment and new processes to help support the integration of these materials, through low volume prototyping, quick turn, rapid prototyping to support R&D and research activities. And again, can't wait to have more communication and discussions in the break about ideas that folks have and the way that they want to innovate and leverage this capability to do prototyping and look at advanced systems. Also, the intent is to push towards pilot production and really mature our process modules and the capability to the point that we can do a low volume production in the facility. So as Whitney said earlier, it's kind of this high mix, low volume facility that can support everything from kind of fundamental research all the way up through low volume production. Tying back to my prior slide, the foundation for all of this is really this core set of integration processes that's going to enable us to work with a very diverse set of materials and go and tackle a very diverse set of application spaces to integrate these materials together to support these microsystems. And so I'll talk a little bit more about that on an upcoming slide, but what's really important here is if you see the banner at the bottom focused on this self-sustaining national capability for 3D HI, R&D, and manufacturing, that self-sustaining piece is really very important to us. We're very, very focused on that, and we're driving towards a position at the end of the program where we have a viable cost model with a self-sustaining capability that's enduring for the use of not only the US government, but again, prototyping to support commercial and dual use applications as well. So we're pushing towards this core set of integration process modules. We've got an initial technology roadmap defined, which I'll share with you here very briefly. And we're also looking down the road at additional technologies that we'll need to support to continue to enable innovation in this space. The 3D Assembly Design Kit, or ADK, and the electronic design automation, the EDA infrastructure that's required to define these systems is clearly very important as well. And so we're pushing and working with those companies to help develop that capability and make sure it's in a position where people can leverage this capability. And then ultimately what's coming out the other side of this is high-performance microsystems spanning a fairly wide range of TRL, as I mentioned, all the way from prototypes through production devices, and then digital twin modeling to support both the development and the manufacture of the components. So now backing up just a touch, I started at DARPA in September of this year, so I'm not quite at a year yet, getting close. It's been an extremely fun year. What an incredible opportunity to have to be there and get to support this program and do as best as I can to keep it moving forward. But before I got there, there was some work done in 2023 and 2024. Really, it was NGMM Phase 0, and it really engaged the community very broadly in the defense space in particular to look at what were the most relevant applications, some very interesting applications for which NGMM would be very, very well suited to help support. And a couple of exemplars came out of that initial study, including a phased array radar, a focal plane array, and a compact power converter. There are actually a couple of variants of these systems, but these 3 exemplars were selected to really drive the initial technology roadmap or the process roadmap for NGMM. They provide some structure for us in the space that is the infinite solution space of 3D-HI. As I mentioned, there's no limit to the innovation and the types of materials that we can integrate and or the approaches to integrate those materials together to form new types of systems. And so these 3 exemplars provided an initial focus for us to help us zero in on developing the initial assembly design kit, the EDA tools that would support that, and then an initial set of process modules and materials that we could work with. And the intent of these exemplars is to help us essentially develop this capability, and they're going to be a proof case for us in maturing the technology and in maturing the processes along the way. So one of the end goal deliverables for our program is really the development and delivery of a working functional system for each one of these exemplars to help us drive the technology. Those exemplars then drive this initial technology roadmap that we've put together. I recognize this is a high-level view of this, and anytime you want to talk details around 3D-HI, inevitably we start talking about interconnect pitch and metallurgy and materials, and you can get down into the details in a real hurry. But this gives some perspective about what our initial technology roadmap is, driven by those exemplars. So you can see here we're working with silicon and glass, gallium nitride, indium phosphide to get kind of a flavor for some of the initial material set that we're starting with, which I would argue is fairly diverse and creates a pretty interesting opportunity with a fairly broad range of applications. And then you also see kind of our initial planned capabilities for bonding. So we're looking at die-to-wafer thermocompression bonding as well as hybrid bonding die-to-wafer. We're also supporting wafer-to-wafer hybrid bonding. Pursuing through substrate vias and a couple of different material sets to support, again, diversity for different integration approaches. And then really importantly, one of the things that's a challenge here is you could imagine taking sort of a brute force approach to deal with this diversity of materials. And in doing so, you could fill mini fabs full of equipment, really to handle every wafer size you could imagine, every material set you could imagine. But ultimately, given that we're really pushing towards the sustainable cost model that will be enduring, we have to be very, very thoughtful about the equipment set that we're installing, the process modules that we're standing up, and how we're going to maintain and sustain those long-term in a viable way. And to that end, we're really looking at pushing towards copper as a common interconnect strategy for us, a common strategy. And so looking at trying to handle the diversity of the wafer sets with wafer reconstitution, so being able to create pocket wafers or other approaches to integrate either other wafers that are sub 200 millimeter wafers and or pieces or components of wafers that might come through multi-project wafer runs or other kinds of technologies, to be able to integrate those and do some post-processing that allows us to bond and tie them together with the other materials that come in. So a lot of innovation going on in this space to come up with this core set of process modules that will allow us to work through a very broad range of applications, again, for both commercial and DoD, but also in a sustainable way as we're moving this forward. And then, of course, one of the foundational pieces here, the Texas Institute for Electronics, before they took on the NGMM program, they were around for about 3 years, and one of their core focus areas was really around innovation for semiconductor manufacturing equipment. They've done research in that space for a very long time, and I think that background and experience that they have is really, really important for NGMM as we, again, continue to explore opportunities, not only in the way that we're developing these process modules and looking at some standards, but also thinking about new ways that you could leverage equipment to deal with this diversity of materials and the integration. I think I covered pretty much everything on the right-hand side. I just wanted to mention that we are headed down a path where we will ultimately have, there are 2 facilities. The one that I showed you on the prior slide is about a 65,000 square foot cleanroom space that's down near the airport in Austin, Texas. That's the Montopolis campus. We also have a research facility that's north of the University of Texas on their research campus that's going to be about 20,000 square feet of cleanroom space once it's fully built out. We've been very, very busy this year supporting a lot of activities both in construction and in installation of equipment and starting to develop all the process modules. But the intent is that both of those facilities will have a very, very similar operational model. They will effectively be run in the same way, and they will support ITAR and EAR fabrication and assembly. So now I'll spend a couple of minutes talking about the plan, the execution plan, where we're at. I'll give you a status update on the kind of the latest and greatest on what's going on. NGMM is divided into 2 phases. They're each 2.5 years. We are about 1 year in. We've just actually crossed over our 1-year anniversary. So we're about 1 year into phase 1. Phase 1 is really about establishing the baseline processes, right? We've got this core set of exemplars that's driving that technology roadmap I showed you. And our goal is to stand up and start to mature and qualify those process modules. It has been a very fun and exciting first year. We are really doing 3 things in parallel. We've got existing facilities that are being refurbished and remodeled and retrofitted to support this new mission. So you can imagine all of the critical infrastructure that you need to support a large-scale fab. And we're in the process of retrofitting, remodeling, and refurbishing all of those critical systems. We're also have been selecting and procuring all of the equipment that will support this mission and installing all of that equipment. And then in parallel, I sometimes smile thinking about, folks waiting for the second that the tool is online to start doing process development on that tool immediately when it's available. And so we're having that happen now where we're doing process development while we're in the process of installing equipment in the same environment. So it's been very, very busy year, but a very fun opportunity to be involved as we're ramping all of this up. But that's the core focus for this year, is standing that up and then making certain that we're driving the development of our assembly design kit, which is effectively the interface and provides the infrastructure to leverage and utilize the capability for the design community, and pushing and driving that capability forward as well. We are starting to talk about, and we have been having some conversations around this, what we're calling a design challenge. DARPA has a very specific construct for something they call a design challenge. In this case, it's a little bit different. What we're really doing here is we really want to engage the community for ideas that folks have of the kinds of systems that we could build with NGMM. And we want to partner with them to actually fund opportunities to build additional exemplars during phase 2. So at the end of phase 1, our intent is to get our assembly design kits set up and in an alpha release version that we can release to the community, and partner with folks who have ideas of additional systems that we can build in phase 2. And so while we're building the exemplars that I showed you in phase 2, we would partner to build these additional systems with the intent to continue to mature the process modules and look for new and innovative ideas for the kinds of systems that we can build. So phase 2 is really focused in that second 2.5 years in building the exemplars, building the kinds of creative ideas that folks have for additional systems that we can build through the design challenge, and maturing all of those process modules to the point that they can support production activities, at least low volume production activities. So really at the end of the program, our end goal really is to enable this again, sort of foundry-based model that's open access for many, many different users to leverage this capability, and to ensure that we have a facility that is cost-effective and available to a broad group of entities that are interested in building these kinds of systems. Now, a quick update on kind of where we are. Like I said, it's been quite a fun year. We've had really just in the last couple of months, we're starting to have hardware come out of the facility, which is super exciting for me. You know, I know for those of you, so I ran the fabs for a few years at Sandia National Labs before I came to DARPA, so I have some background in working in fabs and managing operations. And it just takes a tremendous amount of infrastructure and a tremendous effort to support these kinds of activities, bring this kind of state-of-the-art equipment up and start to do process development. And so it's been really, really fun to see all the pieces come together and to start to get some initial hardware out. As I mentioned, there's a research facility at TI that's north of the university on the research campus. We've been doing some work to expand the existing clean room space that was there, and that's involved retrofit of existing space that was already in the building, as well as building a new central utility building and a gas bunker and a chemical distribution center and some of these kinds of this additional infrastructure to support the larger fab facility. But we've opened up the first phase of clean room space and effectively doubled the clean room space that's there. We've installed all the die wafer hybrid bonding equipment in that facility, and we're starting to get our very first hardware out. We've got some of our initial bonded pairs. We started with fusion bonding, just focused on alignment and qualification of the tools, and we're now doing electrical interconnect of bonded pairs with daisy chains to start to drive and look towards yield for those integrated assemblies. So as I mentioned, it's some complicated times right now as we're moving equipment in as we're doing this bonding, but it's quite exciting to start to see some hardware coming out. And then I've mentioned really a significant focus this first year in getting all of the infrastructure up and ready. And then TI has been extremely busy in ramping up their team, bringing on talent, again, to support some of these challenging areas that we have in thermal and some of these other areas that we need to focus on to stand up the infrastructure, develop the process modules, and really make certain that everything's ready by the end of phase one to support the development of these systems in phase two. A little bit about the design challenge. I think this will provide a little more context for you. I'm quite excited, as I said, to just start to talk with folks now as we get closer to having this capability becoming a reality, to start to get ideas. This is kind of the construct for what we think the design challenge will look like. The block diagram really just lays out an idea of kind of roles and responsibilities, where the intent would be for folks who are interested, partner with DARPA and come up with new designs and new approaches to leverage NGMM. We could fund the design and development of the system and the subcomponents that are required. The performer in that case would pursue and procure the subcomponents, the building blocks, and then partner with TI to do the integration and assembly. TI will have capability to do electrical characterization and test and validation. And so there's certainly an opportunity to do some kind of a joint partnership there for testing and characterizing the devices. And then ultimately for us, certainly we're very interested in the end application and where that might go and the prototypes, but also want to leverage this as an opportunity to continue to improve our infrastructure and the ADK and all of that supports designs moving forward. But really this is a nice opportunity for early engagement with the NGMM Center to start to work with and develop next generation systems. So I think this is my last slide, and really, again, thank you very much for coming to Spark Tank, and I'm quite excited to, during the break, have a little bit of time to talk with you and get some feedback from you on what I've shared today and what your ideas are. But I also want to make you aware of our very first, our inaugural summit event. We're going to host a summit last week of October in Austin. And we really invite people to come down to Texas, come to Austin, learn a little bit more about what we're doing. We really want to update you on the latest and greatest and how we're progressing against the technology roadmap, be able to share some data that's coming off of some of the early hardware that we're building and some of the process development that we're doing. Go into a little bit more depth about our technology roadmap, where we're headed there with that, and just let you have a little bit more insight into the long-term plans. And once again, provide an early opportunity to engage and share your ideas and figure out how you can get involved in designing the kinds of systems or integrating the kinds of systems that we can build with this new capability to really support the next generation of microelectronics. So with that, thank you.